The economics of global warming concerns the economic aspects of global warming. This can inform policies that governments might consider in response. A number of factors make this a difficult problem from both economic and political perspectives. It is a long-term, intergenerational problem. Benefits and costs are distributed unequally both within and across countries, and scientific and public opinions may diverge. One of the most important greenhouse gases is carbon dioxide. Around 20% of carbon dioxide which is emitted due to human activities can remain in the atmosphere for many thousands of years. The long time scales and uncertainty associated with global warming have led analysts to develop scenarios of future environmental, social and economic changes. These scenarios can help governments understand the potential consequences of their decisions. The impacts of climate change include the loss of biodiversity, sea level rise, increased frequency and severity of some extreme weather events, and acidification of the oceans. Economists have attempted to quantify these impacts in monetary terms, but these assessments can be controversial. The two main policy responses to global warming are to reduce greenhouse gas emissions and to adapt to the impacts of global warming. Another policy response which has recently received greater attention is geoengineering of the climate system. One of the responses to the uncertainties of global warming is to adopt a strategy of sequential decision-making. This strategy recognizes that decisions on global warming need to be made with incomplete information, and that decisions in the near term will have potentially long-term impacts. Governments might choose to use risk management as part of the policy response to global warming. For instance, a risk-based approach can be applied to climate impacts which are difficult to quantify in economic terms, e.g., the impacts of global warming on indigenous peoples. Analysts have assessed global warming in relation to sustainable development. Sustainable development considers how future generations might be affected by the actions of the current generation. In some areas, policies designed to address global warming may contribute positively towards other development objectives. In other areas, the cost of global warming policies may divert resources away from other socially and environmentally beneficial investments. Scenarios. One of the economic aspects of climate change is producing scenarios of future economic development. Future economic developments can, for example, affect how vulnerable society is to future climate change, what the future impacts of climate change might be, as well as the level of future GHG emissions. Emissions scenarios. In scenarios designed to project future GHG emissions, economic projections, e.g., changes in future income levels, will often necessarily be combined with other projections that affect emissions, e.g., future population levels. Since these future changes are highly uncertain, one approach is that of scenario analysis. In scenario analysis, scenarios are developed that are based on differing assumptions of future development patterns. An example of this are the SRES emissions scenarios produced by the Intergovernmental Panel on Climate Change. The SRES scenarios project a wide range of possible future emissions levels. The SRES scenarios are baseline or non-intervention scenarios, in that they assume no specific policy measures to control future GHG emissions. The different SRES scenarios contain widely differing assumptions of future social and economic changes. For example, the SRES-A2 emissions scenario projects a future population level of 15 billion people in the year year 2100, but the response.1 scenario projects a lower population level of 7 billion people. The response scenarios were not assigned probabilities by the IPCC, but some authors have argued that particular response scenarios are more likely to occur than others. Some analysts have developed scenarios that project a continuation of current policies into the future. These scenarios are sometimes called business-as-usual scenarios. Experts who work on scenarios tend to prefer the term projections to forecasts or predictions. This distinction is made to emphasize the point that probabilities are not assigned to the scenarios, and that future emissions depend on decisions made both now and into the future. Another approach is that of uncertainty analysis, where analysts attempt to estimate the probability of future changes in emission levels. Global future scenarios. Global futures scenarios can be thought of as stories of possible futures. They allow for the description of factors which are difficult to quantify but are important in affecting future GHG emissions. The IPCC Third Assessment Report includes an assessment of 124 global futures scenarios. These scenarios project a wide range of possible futures. Some are pessimistic. For example, 5 scenarios project the future breakdown of human society. Others are optimistic. For example, in 5 other scenarios, future advances in technology solve most or all of humanity's problems. Most scenarios project increasing damage to the natural environment, but many scenarios also project this trend to reverse in the long term. In the scenarios, Marita et al. Found no strong patterns in the relationship between economic activity and GHG emissions. By itself, this relationship is not proof of causation, and is only reflective of the scenarios that were assessed. In the assessed scenarios, economic growth is compatible with increasing or decreasing GHG emissions. In the latter case, emissions growth is mediated by increased energy efficiency, shifts to non-fossil energy sources, and/or shifts to a post-industrial economy. Most scenarios projecting rising GHGs also project low levels of government intervention in the economy. Scenarios projecting falling GHGs generally have high levels of government intervention in the economy. Factors affecting emissions growth. Historically, growth in GHG emissions have been driven by economic development. One way of understanding trends in GHG emissions is to use the K-year identity. The K-year identity breaks down emissions growth into the effects of changes in human population, economic affluence, and technology. CO2 emissions from energy. GDP per person is used as a measure of economic affluence, and changes in technology are described by the other two terms, and energy-related CO2 emissions, energy use. These two terms are often referred to as energy intensity of GDP and carbon intensity of energy, respectively. Note that the abbreviated term carbon intensity may also refer to the carbon intensity of GDP, i.e. energy-related CO2 emissions, GDP. Reductions in the energy intensity of GDP and/or carbon intensity of energy will tend to reduce energy-related CO2 emissions. Increases in population and/or GDP per capita will tend to increase energy-related CO2 emissions. If, however, energy intensity of GDP or carbon intensity of energy were reduced to zero, increases in population or GDP per capita would not lead to an increase in energy-related CO2 emissions. The graph on the right shows changes in global energy-related CO2 emissions between 1971 and 2009. Also plotted are changes in world population, world GDP per capita, energy intensity of world GDP, and carbon intensity of world energy use over this time period. Reductions in energy intensity of GDP and carbon intensity of energy use have been unable to offset increases in population and GDP per capita. Consequently, energy-related CO2 emissions have increased. Between 1971 and 2009, energy-related CO2 emissions grew on average by about 2.8% per year. Population grew on average by about 2.1% per year and GDP per capita by 2.6% per year. Energy intensity of GDP on average fell by about 1.1% per year, and carbon intensity of energy fell by about 0.2% per year. Trends and projections. Emissions equity and GHG emissions. In considering GHG emissions, there are a number of areas where equity is important. In common language, equity means the quality of being impartial or something that is fair and just. One example of the relevance of equity to GHG emissions are the different ways in which emissions can be measured. These include the total annual emissions of one country, cumulative emissions measured over long time periods, average emissions per person in a country, as well as measurements of energy intensity of GDP, carbon intensity of GDP, or carbon intensity of energy use. Different indicators of emissions provide different insights relevant to climate change policy, and have been an important issue in international climate change negotiations. Developed countries' past contributions to climate change were in the process of economically developing to the current level of prosperity. Developing countries are attempting to rise to this level, this being one cause of their increasing greenhouse gas emissions. Equity is an issue in GHG emissions scenarios. For example, the scenarios used in the Intergovernmental Panel on Climate Change's first assessment report of 1990 were criticized by PARIC. PARIC argued that the stabilization scenarios contained in the report stabilize the lifestyles of the rich and adversely affect the development of the poor. The IPCC's later SRES scenarios, published in 2000, explicitly explore scenarios with a narrowing income gap between the developed and developing countries. Projections of convergence in the SRES scenarios have been criticized for lacking objectivity. Emissions projections. Changes in future greenhouse gas emission levels are highly uncertain, and a wide range of quantitative emission projections have been produced. Rogner et al. Assessed these projections. Some of these projections aggregate anthropogenic emissions into a single figure as a carbon dioxide equivalent. By 2030, baseline scenarios projected an increase in greenhouse emissions of between 25% and 90% relative to the 2000 level. For CO2 only, 2/3 to 3/4 of the increase in emissions was projected to come from developing countries. Although the average per capita CO2 emissions in developing country regions were projected to remain substantially lower than those in developed country regions. By 2100, CO2 EQ projections ranged from a 40% reduction to an increase in emissions of 250% above the levels in 2000. Concentrations and temperatures. As mentioned earlier, impacts of climate change are determined more by the concentration of GHGs in the atmosphere than annual GHG emissions. Changes in the atmospheric concentrations of the individual GHGs are given in greenhouse gas. Rogner et al. Reported that the then current estimated total atmospheric concentration of long-lived GHGs was around 455 parts per million CO2 EQ. The effects of aerosol and land use changes reduced the physical effect of this to 311 to 435 ppm CO2 EQ, with a central estimate of about 375 ppm CO2 EQ. The 2011 estimate of CO2 EQ concentrations, the long-lived GHGs made up of CO2, methane, CH4, nitrous oxide, N2O, CHLORO, FLUORO, CARBO, N12, CFC11, and 15 other halogenated gases, is 473 ppm CO2 EQ. The NOAA estimate excludes the overall cooling effect of aerosols. 6 of the SRES emissions scenarios have been used to project possible future changes in atmospheric CO2 concentrations. For the 6 illustrative SRES scenarios, IPCC projected the concentration of CO2 in the year 2100 as ranging between 540 and 970 parts per million. Uncertainties such as the removal of carbon from the atmosphere by sinks increase the projected range to between 490 and 1260 ppm. This compares to a pre-industrial concentration of 280 ppm and a concentration of 390.5 ppm in 2011. Temperature. Atmospheric GHG concentrations can be related to changes in global mean temperature by the climate sensitivity. Projections of future global warming are affected by different estimates of climate sensitivity. For a given increase in the atmospheric concentration of GHGs, high estimates of climate sensitivity suggest that relatively more future warming will occur, while low estimates of climate sensitivity suggest that relatively less future warming will occur. Lower values would correspond with less severe climate impacts, while higher values would correspond with more severe impacts. In the scientific literature, there is sometimes a focus on best estimate or likely values of climate sensitivity. However, from a risk management perspective, values outside of likely ranges are relevant because, though these values are less probable, they could be associated with more severe climate impacts. Analysts have also looked at how uncertainty over climate sensitivity affects economic estimates of climate change impacts. Hope, for example, found that uncertainty over the climate sensitivity was the most important factor in determining the social cost of carbon. Cost-benefit analysis. Standard cost-benefit analysis can be applied to the problem of climate change. This requires the valuation of costs and benefits using willingness to pay or willingness to accept compensation as a measure of value, and a criterion for accepting or rejecting proposals. For in CBA where WTP, WTA is used, climate change impacts are aggregated into a monetary value, with environmental impacts converted into consumption equivalents, and risk accounted for using certainty equivalents. The values over time are then discounted to produce their equivalent present values. The valuation of costs and benefits of climate change can be controversial because some climate change impacts are difficult to assign a value to, e.g., ecosystems and human health. It is also impossible to know the preferences of future generations, which affects the valuation of costs and benefits. Another difficulty is quantifying the risks of future climate change. 4. The standard criterion is the compensation principle. According to the compensation principle, so long as those benefiting from a particular project compensate the losers, and there is still something left over, then the result is an unambiguous gain in welfare. If there are no mechanisms allowing compensation to be paid, then it is necessary to assign weights to particular individuals. One of the mechanisms for compensation is impossible for this problem. Mitigation might benefit future generations at the expense of current generations, but there is no way that future generations can compensate current generations for the costs of mitigation. On the other hand, should future generations bear most of the costs of climate change, compensation to them would not be possible. Another transfer for compensation exists between regions and populations. If, for example, some countries were to benefit from future climate change but others lose out, there is no guarantee that the winners would compensate the losers. Similarly, if some countries were to benefit from reducing climate change but others lose out, there would likewise be no guarantee that the winners would compensate the losers. Cost-benefit analysis and risk. In a cost-benefit analysis, an acceptable risk means that the benefits of a climate policy outweigh the costs of the policy. The standard rule used by public and private decision-makers is that a risk will be acceptable if the expected net present value is positive. The expected value is the mean of the distribution of expected outcomes. In other words, it is the average expected outcome for a particular decision. This criterion has been justified on the basis that a policy's benefits and costs have known probabilities. Economic agents can diversify their own risk through insurance and other markets. On the first point, probabilities for climate change are difficult to calculate. Also, some impacts, such as those on human health and biodiversity, are difficult to value. On the second point, it has been suggested that insurance could be bought against climate change risks. In practice, however, there are difficulties in implementing the necessary policies to diversify climate change risks. One of the problems of climate change are the large uncertainties over the potential impacts of climate change, and the costs and benefits of actions taken in response to climate change, e.g., in reducing GHG emissions. Two related ways of thinking about the problem of climate change decision-making in the presence of uncertainty are iterative risk management and sequential decision-making. Considerations in a risk-based approach might include, for example, the potential for low-probability, worst-case climate change impacts. An approach based on sequential decision-making recognizes that, over time, decisions related to climate change can be revised in the light of improved information. This is particularly important with respect to climate change due to the long-term nature of the problem. A near-term hedging strategy concerned with reducing future climate impacts might favor stringent, near-term emissions reductions. As stated earlier, carbon dioxide accumulates in the atmosphere, and to stabilize the atmospheric concentration of CO2, emissions would need to be drastically reduced from the present level. Stringent near-term emissions reductions allow for greater future flexibility with regard to a low stabilization target, e.g., 450 parts per million CO2. To put it differently, stringent near-term emissions abatement can be seen as having an option value in allowing for lower, long-term stabilization targets. This option may be lost if near-term emissions abatement is less stringent. On the other hand, a view may be taken that points to the benefits of improved information over time. This may suggest an approach where near-term emissions abatement is more modest. Another way of viewing the problem is to look at the potential irreversibility of future climate change impacts against the irreversibility of making investments in efforts to reduce emissions. Overall, a range of arguments can be made in favor of policies where emissions are reduced stringently or modestly in the near term. Resilient and adaptive strategies. Granger Morgan et al. Suggested two related decision-making management strategies that might be particularly appealing when faced with high uncertainty. The first were resilient strategies. This seeks to identify a range of possible future circumstances, and then choose approaches that work reasonably well across all the range. The second were adaptive strategies. The idea here is to choose strategies that can be improved as more is learned as the future progresses. Granger-Morgan et al. Contrasted these two approaches with the cost-benefit approach, which seeks to find an optimal strategy. Portfolio theory. An example of a strategy that is based on risk is portfolio theory. This suggests that a reasonable response to uncertainty is to have a wide portfolio of possible responses. In the case of climate change, mitigation can be viewed as an effort to reduce the chance of climate change impacts. Adaptation acts as insurance against the chance that unfavorable impacts occur. The risk associated with these impacts can also be spread. As part of a policy portfolio, climate research can help when making future decisions. Technology research can help to lower future costs. Optimal choices and risk aversion. The optimal result of decision analysis depends on how optimal is defined. Decision analysis requires a selection criterion to be specified. In a decision analysis based on monetized cost-benefit analysis, the optimal policy is evaluated in economic terms. The optimal result of monetized CBA maximizes net benefits. Another type of decision analysis is cost-effectiveness analysis. Cost-effectiveness analysis aims to minimize net costs. Monetized CBA may be used to decide on the policy objective, e.g., how much emissions should be allowed to grow over time. The benefits of emissions reductions are included as part of the assessment. Unlike monetized CBA, cost-effectiveness analysis does not suggest an optimal climate policy. For example, cost-effectiveness analysis may be used to determine how to stabilize atmospheric greenhouse gas concentrations at lowest cost. However, the actual choice of stabilization target is not decided in the analysis. The choice of selection criterion for decision analysis is subjective. The choice of criterion is made outside of the analysis. One of the influences on this choice is attitude to risk. Risk aversion describes how willing or unwilling someone is to take risks. Evidence indicates that most, but not all, individuals prefer certain outcomes to uncertain ones. Risk-averse individuals prefer decision criteria that reduce the chance of the worst possible outcome, while risk-seeking individuals prefer decision criteria that maximize the chance of the best possible outcome. In terms of returns on investment, if society as a whole is risk-averse, we might be willing to accept some investments with negative expected returns, e.g., in mitigation. Such investments may help to reduce the possibility of future climate damages of the costs of adaptation. Alternative views. As stated, there is considerable uncertainty over decisions regarding climate change, as well as different attitudes over how to proceed, e.g., attitudes to risk and valuation of climate change impacts. Risk management can be used to evaluate policy decisions based on a range of criteria or viewpoints, and is not restricted to the results of particular type of analysis, e.g., monetized CBA. Some authors have focused on a disaggregated analysis of climate change impacts. Disaggregated refers to the choice to assess impacts in a variety of indicators or units, e.g., changes in agricultural yields and loss of biodiversity. By contrast, monetized CBA converts all impacts into a common unit, which is used to assess changes in social welfare. International insurance. Traditional insurance works by transferring risk to those better able or more willing to bear risk, and also by the pooling of risk. Since the risks of climate change are, to some extent, correlated, this reduces the effectiveness of pooling. However, there is reason to believe that different regions will be affected differently by climate change. This suggests that pooling might be effective, since developing countries appear to be potentially most at risk from the effects of climate change. Developed countries could provide insurance against these risks. Authors have pointed to several reasons why commercial insurance markets cannot adequately cover risks associated with climate change. For example, there is no international market where individuals or countries can insure themselves against losses from climate change or related climate change policies. Financial markets for risk. There are several options for how insurance could be used in responding to climate change. One response could be to have binding agreements between countries. Countries suffering greater than average climate-related losses would be assisted by those suffering less than average losses. This would be a type of mutual insurance contract. Another approach would be to trade risk securities among countries. These securities would amount to betting on particular climate outcomes. These two approaches would allow for a more efficient distribution of climate change risks. They would also allow for different beliefs over future climate outcomes. For example, it has been suggested that these markets might provide an objective test of the honesty of a particular country's beliefs over climate change. Countries that honestly believe that climate change presents little risk would be more prone to hold securities against these risks.